Hello, everyone. We are on to one of our last calculation concepts of this week because the podcast after this one is all going to be about a technique we can use in the lab. This is Dalton's law of partial pressures. And this is actually super logical. It's pretty rare that we have a gas that is all by itself. Normally, in the real world, things are mixtures. Think about the air that you're breathing in and out right at this moment. So as you're breathing in and you're breathing out, there's a massive mixture going on. Yes, of course, there's oxygen in there, but there's quite a large amount of nitrogen going in and out. There's a small bit of water vapor. You've got carbon dioxide, of course, and then we've got some things like just argon that are hanging out there going in and out, and hydrogen in and out as well. So it's a mix. And of course, within that mix, you have a total pressure associated with it, right? So there's a pressure in the room right now that you're sitting in. But that total pressure is made up of all the other gases being added up together for their pressures. So the pressure of the oxygen gas, the pressure of the nitrogen gas, the pressure of the hydrogen gas, etc. Now this will vary. If there's only two gases mixed together, well, there's only two different partial pressures of gases that make up the total. If there's 10 gases mixed together, of course you're going to have 10 partial pressures that are all individually added up together to get the total overall pressure. Now, this formula, guys, isn't on your formula sheet. It's a pretty logical one, but it's one that you should memorize. Ultimately, the P1, P2, P3, etc., this is going to change depending upon how many gases are in the situation that we're using. Be logical about this. If you have a lot of a particular type of gas, of course it's going to have a bigger contribution. Take this type of a diagram and consider it. We have the pressure of hydrogen gas contributing 2.9 atmospheres. So atmospheres is just another pressure measurement. All right. Vice versa, we've got another one that's contributing, and this is helium. Helium's contributing quite a bit more, 7.2 atmospheres. And notice there's a greater amount of helium than there is of hydrogen, right? 1.50 moles of helium versus only 0.6 of the hydrogen. Logically then, when we add those two together, there's nothing meant to be difficult about this. Take the pressure of the hydrogen, add it to the pressure of the helium, and you will get the total pressure. Amounts work the same way. The amount of the hydrogen plus the number of moles, the amount of the helium, gives us the total number of moles. Other parts of this, though, stay constant, and that's important to notice. 5 liters is our volume, and that's how much is there. 5 liters is the volume of the helium too. And when we put them together, they're still in a 5-liter container. So volume is the same for both. Also take note, temperature, 20 degrees Celsius, 20 degrees Celsius, and 20. So pressure and temperature volume and temperature are the same for both of them. The amount of pressure gets added up. And, of course, the amount of moles also gets added up. Look at this scenario. Similar type 1, where we have our first gas, gas A. We have our second gas, gas B. Add those together, and we get the total. 1 atmosphere plus 3 atmospheres. Ooh, check it out. 4 atmospheres. The partial pressures add up to the total pressure. Let's put this into practice. Here's your example. The key thing that you have to catch when reading a question like this is that more than one type of gas is present. Nitrogen gas is being mentioned, and carbon dioxide gas is mentioned as well. And each of them have their own amount. There's 50 grams of nitrogen gas, and there's 50 grams of carbon dioxide. All right. In terms of consistencies, the volume's the same. It's 10 liters for both. The temperature's the same. It's 20 degrees Celsius for both. The goal of your question is to calculate the partial pressure of each and then get the total. How do you do that? Well, adding the two partial pressures together. These questions can get fairly long because you're dealing with information where you have to really do calculations for two separate gases. So let's start with nitrogen. Usually what I'll do is I'll write out the actual formula to keep myself organized. Remember, nitrogen is part of Hofbrinkel, so it's N2 gas. Now when you're writing down everything that applies, well, the first one, of course, is volume. Volume is 10.0 liters. Temperature is 20 degrees Celsius, so add that to 273.15. We have 293.15 Kelvin as our temperature. Keep going. R, of course, is same as usual, 8.314 liters per kilopascals divided by mole per Kelvin. And pressure is our goal. Now, we don't have enough information to use PV equals nRT yet. We got to get N. But there is enough information to figure it out. Mass is given to you, 50.0 grams, and we know the gas, it's N2. So that means you can figure out the molar mass. Take that 14.01 times it by 2, we get 28.02 grams per mole. Okay, these two things together we can take in order to figure out, of course, what N is. N equals mass over molar mass, 50 grams, divided by 28.02 grams per mole. Remember not to round this number. You're going to have to use it again. N is equal to 1.784 moles. Alrighty, we're getting somewhere now. From here, we can continue to actually figure out what the pressure is equal to. Pressure comes into the universal ideal gas law, PV equals nRT, and we need to isolate RP. So divide by V, V's cancel out. P is equal to nRT over V. N we figured out before, 1.78 moles. R, 8.314 liters times kilopascals over moles times Kelvin. All of that times that temperature of 293.15 Kelvin. And that whole thing is divided by volume, 10.0 liters. Once you work all through that, we're going to get an end result wonderful answer of 435 kilopascals. Now remember, this is the pressure specifically of nitrogen gas. So I'm going to write a little N2 there because you have to recognize what you just found was the partial pressure. Now, that's part of the question. When you calculate the total pressure, though, you really need to use the unrounded value because think about it. We want the total pressure to be accurate as well. So the unrounded value is 434.9124 ... kilopascals. Keep that in the back of your head when we do the total. Okay, let's move on and figure it out for carbon dioxide. So CO2 gas, again, write out our formula. Let's start going step by step. The volume remains consistent, 10.0 liters. The temperature remains consistent, 293.15 Kelvin. R, of course, is R. Once again, we're looking for pressure. Here's our unknown. But the good news is you've got your mass in the question, 50.0 grams, and you can calculate the molar mass. Take the carbon molar mass plus 2 oxygens molar mass, we get 44.01 grams per mole. N is equal to mass over molar mass, so 50.0 grams divided by 44.01 grams per mole. The answer to N here, and again, don't round this, you're going to need to use it again, 1.1361 ... moles. There's our N. Exact same process as what you used when we figured out nitrogen, but now we're on the CO2. So we're still going PV equals nRT, and we can isolate that P in order to figure out the pressure for the question. Pressure is equal to N, which you just found, 1.1361 moles, times R, 8.314 liters, times kilopascals over mole times Kelvin, times the temperature, 293.15 Kelvin, all of that divided by your volume, 10.0 liters, equals, again, you're going to want both values here. The unrounded value, 276.89719 ... kilopascals. But the partial pressure of CO2, which is part of the question that it's asking for, is that rounded value, 277 kilopascals. Okay, look at what we've got. We were able to get N, use it again in order to find the partial pressure of carbon dioxide. Previously, we were able to find the partial pressure of nitrogen. This is all we need to now get the total pressure. So when you calculate your total pressure, we're going to take the pressure of that nitrogen gas, add it to the pressure of the CO2 gas, and then we can get P total. Remember, unrounded values, 434.91 ... kilopascals for nitrogen, plus what we just got for CO2, 276.89 ... kilopascals. Add those two together, and P total is going to be 712 kilopascals. Done and done. So really, guys, this is so similar to the questions that you were doing before. The difference is that instead of you just figuring out an individual gas pressure and being done with it, we have to take into consideration that you can add those together to get a total. Okay, let's look at the next example. I'm not going to work this one out in full, but I'll give you enough information to be able to go through it. Now, huge hints again that are there. Contains fluorine gas and chlorine gas. As long as you notice that there are two different pressures there, that that are definitely going to be aware that they are going to come together to make a total pressure. Okay, this question is slightly different in that you're given a total pressure, right? 1,500, 1,500 kilopascals is P total. Remember those consistencies. Volume is the same no matter what. Temperature is the same no matter what. You've also been given in this question a partial pressure of the chlorine gas. So we do know P2. So think about it. We've got P2, we've got the total pressure. You then absolutely have enough information that you can calculate P1. And honestly, that's your first step here, is you need to find the partial pressure of the fluorine gas. So hint in terms of how to do that. If pressure of fluorine is what we don't know, that's going to be added to the pressure of chlorine, which we do know, which will equal the total pressure. So again, pressure of fluorine is our unknown, plus pressure of chlorine, 450 kilopascals, is going to equal the total pressure, 1,500 kilopascals. We need to get that fluorine by itself. This one. Simple algebra. You're adding 450, so we need to do the opposite. Subtract 450 kilopascals. What you do to one side, you do the other. On the left-hand side of the equation, those will cancel out. On the right-hand side, we end up with the pressure, partial pressure, of fluorine gas is 1,050 kilopascals. Perfect. This is super helpful because now we have a pressure associated with each one. Now consider back to the actual goal of the question. We're trying to figure out what the mass of each gas is. Now mass, of course, is related to amount. I'm going to switch pages here to keep going. So if mass is related to amount, because N is equal to mass over molar mass, which means mass is equal to number of moles times molar mass. Well, as long as I have a way that I can figure out the number of moles, then I'm going to be good to go to get mass. Now you've got two different things that you have to work with. So you're going to have to find the mass of the fluorine gas, and you're going to have to find the mass of the chlorine gas. So there's two separate questions that are happening. For both of those, PV equals nRT is absolutely going to work. Rearrange it so that you get N by itself. N is equal to PV over RT. Oh, exact same thing happens over here. PV equals nRT, and we have the partial pressures. We have the pressures now of fluorine and chlorine. One of them was given to you in the question, the other one you just determined. N is equal to PV over RT. Once you calculate what N is, N and N, well, then from there you're going to be good to go, no problem, to recognize that the mass, I simply have to take that N that I found and multiply it by the molar mass of fluorine. Same thing for chlorine. For mass, I'm going to have to take the N that I found and multiply it by the molar mass for chlorine. When you do that, don't forget, fluorine is diatomic. You need to take the molar mass and times it by 2. Chlorine's the same, diatomic. Take the molar mass, times it by 2. When you do that, guys, and work it all out, you will get a mass of fluorine gas equal to 198 grams. So try it out, check your answer, and you will get a mass of chlorine gas out of 158 grams. If you're struggling with that at all, the PDF of the notes has the total calculations step by step. But I feel like this is a good stepping stone that you can work through, as long as you recognized that you had to get the partial pressure of fluorine gas first, and then you could keep on going. That's it for this lesson. We have one more podcast this week, which relates to an application in the lab. Otherwise, have a good rest of your day.